All right, so the last model that we're going to talk about is a geometric model. Now, we spent a lot more time on the binomial model because it's a lot more important. The formula's harder, and a lot of our analysis in second semester is it has its foundation in the binomial model. Geometric model is still, kind of interesting. It's just the formula is easier, so you don't really need to memorize the formula at all. It's not on the formula sheet, and it doesn't have as many consequences in future stuff, but you're still responsible for it, so let's go over it. A geometric setting arises when we perform independent trials of the same chance process and record the number of trials it takes to get one success, to get your first success. On each trial, the probability P of success must be the same. So if we were checking our bins, binary, success failure, it's good. Independent, got to have independent trials, good. Same probability of success, that's good. This one, however, fails. We don't have a set number of trials. Instead, we keep doing it until we get our first success and then we stop. Might happen after the first trial. Might take us 100 trials. And also, importantly, we record the number of trials to get our success. We don't record the number of successes out of 10. So it's just a different model. So if a variable follows this situation and we record this, we call it a geometric random variable, and the distribution of the probabilities will be called the geometric distribution. So let's do a geometric problem. You're going to see that we don't even really need to identify it. In fact, we've done ones like this already. The probability that the kitchen serves those fantastic snickerdoodle cookies for lunch on a given day is 0.3. So that's the probability of the success. So Q would be the probability of a failure. That means there's a 70% chance we don't get the good cookie. Find the probability that it takes 4 days to finally get the good snickerdoodle cookies. You get the snickerdoodle on the 4th day. So what's the probability? So this is a geometric model. Number of days to first snickerdoodle cookie. So let's find the probability that y is equal to 4. What's the probability it takes 4 days before we get our first success? Well, we have to get a failure on the first. I guess I'll write this as I'm just going to write it. You got to get a failure on the first, 0.7, a failure on the second, and we have independence, right? Well, I don't know if we have independence here. I'm going to assume independence. Question should say assume independence. Sorry, I sometimes forget. So the probability is still going to be 0.7. Third day, 0.7. And then on the 4th day, we have to get our snickerdoodle cookie. So 0.7 to the third times 0.3. 10%. So there's a 10% chance that we have to wait until that we get our first cookie on the 4th day. This is geometric. I didn't need to use the formula. You just use common sense. That's what's kind of nice about the geometric model. Okay? So here's the probability formula. This is not on the formula sheet. Note this formula is not on the formula sheet. And you shouldn't memorize it. The probability that your successes is equal to 4 is equal to k is, well, if you get your first success on the kth attempt, that means you have to have k minus 1 failures. So q to the k minus 1 times your one success. I would not memorize that at all. Calculator functions. Well, if you use the geometric PDF and you put in the probability and the number of successes, it'll calculate it for you. Just to illustrate that we get this 10% menu statistics. By the way, I would never use the geometric PDF because it's so easy you don't even need to. But let's illustrate it. That's H. Probability of success is 0.3. And what's the probability we get our first success on the 4th day? So they just wrote a program to calculate this for us in the background. Not really needed. Note, the formula is so easy, the calculator-related function isn't really needed. However, sorry, I lost my train of thought here. However, the CDF can really save us some time, because the CDF is going to calculate the CDF is going to calculate all the probabilities from a lower bound to an upper bound. Verify the function. Okay, I already did that. Okay, so this is the mean or expected value of the geometric random variable. These are not provided on the formula sheet, and technically, I don't know if you really need to know it or not. It's kind of, the mean is kind of common sense. You should kind of understand that. Standard deviation, you definitely do not need to know. And I'm not going to even, I don't even know if I'm going to do an example with it, but we'll see. So if y is a geometric random variable with a probability of success p, then the mean or expected value is 1 over p. So it might not look real, it's pretty obvious. The probability that you roll a dice and you get a 3 is 1 out of 6. So how many times would you expect to have to roll it until you get your first 6? Probably not getting it on the first one. If I asked you how many times would you expect to have to roll it, you'd probably say 6, right? If I get it 1 out of 6 times, then it's going to take me 6 times on average to get it. So that's just the reciprocal of my probability. That's all this is saying. And I think you should know that. I'll say you're responsible for that on the test. The standard deviation, however, is definitely not. The standard deviation is the square root of q over p. I don't know where that really even comes from. I've never really looked at it or done much with it, so not responsible for that. Suppose 25% of a large community considers themselves Dallas Cowboys fans. We randomly select people at random from this community and ask them if they are Cowboys fans. Let y equal the number of people that must be selected to get the first Cowboy fan. Can we assume independence between each selection of fans? So first of all, do we have independence? If the first person is a Cowboys fan, does that change the likelihood that the second person is? Yes. We have a large community, but it's finite. If you take one person out of that community, it's going to change the likelihood a little bit for the next one. However, I think it's fair to assume that, how many people are we selecting? Oh, we're not selecting a set number of people. Oof. So we don't really have an n. Well, I guess what I'm going to say is, for reasonably small values of n, n is going to be less than 10% of the population. 10% of all Dallas Cowboy fans. I mean, there's probably hundreds of thousands of Cowboys fans. I'm going to get my first success in the first, 3, 4, 5, 6, 7, 10, 20, even 100. So any reasonable sample size that I would pick is going to be less than 10% of all fans. So the 10% condition passes. And although technically I don't have independence, but I can kind of assume that I have this pseudo independence, and I can assume that if I use the geometric model, it'll be approximately correct. Find the probability that we have to select 4 people before we find the first Cowboy fan. So this is a probability that you get your first success on the 4th fan. That means you got to get not a Cowboy fan on the first, not a Cowboy fan on the second, third, and then you get your Cowboy fan on the 4th. Let's type that in our calculator. 0.75 to the third times 0.25, 10.5%. Find the probability that we have to select 6 people or more before we find the first Cowboy fan. So let's look at our probability model. These are our y's. These are our probability of y's. The smallest number of outcomes that could happen is 1. The earliest you can get that first fan is on the first pick. You can't get it on the 0th pick. So it's going to be 1, 2, 3, 4, 5, 6, 7. Now this model actually theoretically goes to infinity. I want, why is my battery dying? I gotta check my battery. Okay, there we go. I want the probability that we get our first cowboy fan. We have to select 6 or more. So we get it on the 6th or greater than the 6th. That's all of these added together. What makes this kind of hard is I can't really add them all together because it goes to infinity. So what I'm going to do is I'm going to say this is equal to 1 minus the probability of these. And this is not so bad because this is just 5. So this is what I'm using the rule of complements. This is 1 minus the probability that y is between 1 and 5 inclusive. Now I can just add up these 5 rather than add up these infinite number. But this is where the geometric CDF works kind of nice. The CDF goes from the lower bound to the upper bound. Did I cover it up here? CDF goes from the lower bound to the upper bound. So let's just use that. This is going to be equal to geometric CDF. Probability of success is 0.25. Lower bound is 1. Upper bound is 5. And let's not forget, I need to take 1 minus that number. So this is going to be 1 minus, let's go to that CDF, I, 0.25, 1 to 5, 0.237. Find the mean and standard deviation. The mean you're responsible for. This is going to be 1 over p, which is 1 over 1/4, which is 4. The standard deviation, like I said, I don't even know. I know it's got a square root of q over p, p over square root of q over p. That's the square root of q is 0.75 over p is 0.25. One of these days I'm going to look that up and figure out what that's from, but oh well, not today. .46. Okay. In the calculator, create a probability distribution for y and display the distribution using a histogram. All right, so I'm going to do this really quickly. Again, why this is hard is because the model, the outcomes actually go to infinity. And I can't make the outcomes go to infinity. So I'm just going to make them go pretty big. How big? I don't know. Should we go like maybe 100 or something? 200? So let's just generate n, initial term 0. I'm going to start from 0 and go to 200. I'll do 200 outcomes. Why did I start at 0? Dang it. It's supposed to start at a 1. Let's calculate the probabilities. Menu, statistics, distributions. Go down to geometric. PDF, because I want an individual value, not the cumulative. Success, 0.25. Value, pull up off those rows. So let's look at our y's versus our plot properties, 9, our probabilities. Let's change our bin settings to be 1. So the probability that you have to get 120 people before you get your first Cowboys fan is almost nothing. It's not going to take you 40 even. It's not even really going to take you 20. Here's what the model looks like.